So what I did in the lab, I was in the lab, what I did, the first thing is I thought of, it's the input matching network, 8 dB noise figure, it has to be coming from the input matching network of the device. So I took a diamond scriber and I cut the input matching network. I cut here and I cut on the input of my circuit. And just to connect my input to the FET, I went ahead in the lab and I soldered. I put soldered wire. It's a loop of wire I found sitting at the bench in the lab, and I just soldered it to connect the input to the FET and completely eliminate the input matching network. So I went ahead and did it, and I'm really glad I just like this idea came into my mind, because surprisingly, without even knowing, I watched the noise figure meter in the lab, and it started going down from 8 to 7 to 6 to 5 to 4 and all the way down to 0.5 dB noise figure. I said, wow, what is happening here? I'm getting 0.5 dB noise figure from something that I haven't even thought of, or just like random selection of putting a wire between the input of the FET to the input of the circuit. This is unbelievable for me at that time. So basically, what I wanted to do, now that I got my 0.5 dB noise figure with this loop of wire, and this is basically what I did to the circuit. You can see I diamond scribed here, I diamond scribed here, open, and I put that loop of wire from input to the FET input, where the FET sits. So basically what I did, now it's time to go back to my office, back to the drawing board, and I want to understand what is about this loop of wire that helped me achieve that 0.5 dB noise figure. And surprisingly, by doing investigation on this, I learned a lot of things at that time. I took those matching networks that I mentioned to you earlier on, including the one that I built, and I plotted the impedance of the matching network itself between 2 and 3 gigahertz. So you can see how wide the matching network impedance between 2 and 3 gigahertz, where the red area is the impedance, the optimum noise impedance of the FET between 2 and 3 gigahertz, and that dot in the middle of the red region is 2.4 gigahertz. So it's true, both this impedance, the matching network impedance, and the device optimum noise impedance, you can see at 2.4 gigahertz they meet. And when I simulate at 2.4 gigahertz, I am getting the optimum noise figure from the device. But a little bit of deviation from that 2.4 gigahertz, you can see that my matching network, this matching network, goes all over the Smith chart, away, far away from that minimum noise figure region, the red region. And this matching network also does the same thing. And this one, the open stub and quarter wavelength, even it's worse. It goes farther apart from that red region. So you can see that those topologies that I used are very sensitive, and any small process variation in my design will take me far away from this optimum red region, optimum noise figure region. But what about the wire that I put, that loop of wire? I went ahead and investigated this, and that loop of wire is represented here by a very high impedance, single line 120 ohm impedance. Basically it's a highly inductive line. And you can see, plotting in the black color, plotting the impedance of this line lies between 2 and 3 gigahertz, lie within the red region, the optimum noise figure. It does not go far away from that optimum noise figure region. This is why it was very easy to tune. It was very easy to get that 0.5 dB noise figure in the lab once I put that wire, which is basically, to implement it in MIC circuit, you need a very high impedance, like 120 ohm MIC line on alumina substrate. And some of you might ask, how do you implement this? This is going to be so narrow to get 120 ohm. It's not realizable in MIC. And basically what we did, we made it realizable by using the suspended line concept. So basically we etched the ground plane under that line and made the line over the alumina suspended in like air underneath it rather than a ground plane underneath it. And that gave the much higher impedance to this line. And believe it or not, when we built those LNAs, we built many of them, and in the lab we have to tune them. We tuned them so quickly, like popcorn. I mean, just like so quickly, the technician in the lab did not have any problem tuning them. It's like every amp, just 1 minute, test it, it meets specs, and ship it. This is another way just to show that this is the optimum noise figure that I needed at 2.4 gigahertz, and this line, which is a low Q, brought me to 50 ohm, and you can see it's under Q equal 1. So the Q is very low and it's not sensitive. I can even improve on this circuit if I can have even a much higher impedance, like a 250 ohm line followed by an 89 ohm line. But obviously those are not realizable, but I showed you that this is realizable by using the suspended line concept. This is just another way to look at the design. So we have noise figure versus frequency for many different matching networks. And you can see the one on the bottom, the noise figure stays low between 2 and 3 gigahertz, is that single line matching, which we discovered by luck in the lab. So the point I'm trying to make here, it's the topology of the matching network that made a big difference here. Which matching network we use is what really made the big difference in the yield. Then another example, we went to MIMIC, from MIC to MIMIC, real design examples. We had a wafer, we put 2 amplifiers at X-band, 2 X-band amplifiers. One used standard design technique. The other one, it did use the DFM techniques, or design of experiments techniques. Both amps are the same size, they use the same device, same process, same wafer. The only difference is amp 2 went through that DFM, DOE-based design technique, where amp 1 did not. It used the standard design technique. And this is the wafer probed results. You can see the variation in the gain, and you can see the consistency in the gain of amp 2. Very consistent, higher yield, and also the foundry at that time, the foundry process shifted a little bit to lower frequency. The process at that time. Notice that this design, the S22, shifted much further to lower frequency than this one. This one is less sensitive. It shifted because the whole process shifted at that time, but it still worked. Even the process at that time in the foundry shifted a bit to the left. Okay, so it makes a big difference to use the DFM-based methodology or design of experiments. Then taking that amplifier and expanding it into a macro cell, we designed the mixer now. Up converter number 2 uses a mixer design using that DFM technique, where up converter 1 has the standard design again. And I showed you this earlier. This is the amp and the mixer together. You can see the consistency and the high yield when you use that DFM-based technique compared to the standard design, which did not go through the DFM design process. So it's really worth it. You put some time up front in your design process before you even go into the physical design, before the layout, just up front to make sure that you have the right topology that is not sensitive, and it really makes a big difference in the outcome. You will get first pass success, you will get high yield, you will get first to market, and insensitive design to power supply and temperature variations.